All right, so last time we introduced a new concept, electric potential energy, because the electric force is a conservative force, right? There's a fundamental theory in physics. For any conservative force, you can always define a potential energy associated with this conservative force. And this is the definition of potential energy, right, based on that fundamental theory. And then we also define another thing called potential, because the potential energy has the task charge, the information of task charge there, right? If I want to calculate the potential energy of any task charge, right, I have to use the information of task charge. But I want to define something that only depends on the electric field itself, the source charge, right? It's pretty much like this E we define, right? It's only going to be determined by the source, right? Has nothing to do with the charge, task charge you bringing to this electric field. So that's why the simplest definition is just going to be this, right? You just divide the potential energy by Q naught. So you're going to divide this Q naught by this Fe, then you just get E in this integral, right? So this thing we define potential is going to be totally dependent on, it only depends on the electric field itself. Right? So if I set a zero reference point, the potential at every single point, it's going to be a unique number, right? Once the electric field has already been set up. But then, if you want to find the potential energy of a task charge you bring at point A or point B, you would just do potential energy times Q naught times potential, right? So it's pretty much like the relation between the force and the electric field, right? Once we define electric field, okay, and then we find the fundamental theory to calculate the electric field, okay, from any sources, then calculating the electric force is going to be very easy, right? This is going to be the hard part, right? And the theory we found is this, right? We started with a point charge, right? We found the theory for point charge, then we generalize it to a group of isolated point charges and also continuous distribution of charge. Then that's the theory. That's the fundamental theory to calculate electric field. That's the hard work. Once you have done that, calculating the force is going to be easy, right? Now the electric potential and energy, they're the same relation, right? So now our focus is going to be shifted to this potential. If you can find a fundamental theory to calculate the potential created by any kind of electric field, then calculating the potential energy of any task charge you bring into this electric field is going to be super easy, right? You just multiply the task charge by this potential, right? But still, you have to find a fundamental theory to calculate the potential for any electric field. So that's the hard part. We will do that, okay? And that's the reason we define electric potential, any electric potential energy. So we're going to shift our focus to this guy, okay? So again, use the gravity as an energy, okay? So we could have defined, so this is how we defined gravitational potential energy, right? We could have defined a gravitational potential, okay, like this. So if you remove the information of this object, right, so this GH, it's going to be what we would call gravitational potential energy. And this thing is totally determined by the gravity, right? For example, if it's an gravitational field created by the Earth, this 9 point A, it's going to be always there. And then the height, once you have picked a zero reference point, the height is also going to be a unique number. So the potential at any point is going to be fixed. Once you have this potential, then how do you find the potential energy? You just multiply the mass by this potential energy, right? The mass still determines on the object you bring into this gravitational potential energy, okay? So, and then of course, electric potential, this V still going to be a scalar, okay? It's no direction, so that's another reason we wanted to introduce potential and potential energy. We want to study them. They are scalars. Everyone prefers scalars than vectors, right? Electric field, force, they're nice, but they are vectors, right? We prefer, if there's a choice, I prefer to work with scalars, okay? So potential energy, they're both scalars, very nice to work with, okay? And of course, only the difference is meaningful, right? The actual value of a potential, the V at a certain point, totally depends on the zero reference you pick. So the problem must tell you a zero reference if the problem wants you to calculate the potential at a specific point or a potential energy, right? So that's why the potential at any point can be positive or negative. Don't freak out if you see negative numbers in physics. These signs, they're meaningful, okay? Don't just erase that. Don't just assume everything is positive, okay? So in this case, a joule actually is it's a very large unit in atomic or subatomic scale, okay? So in this scale, another unit, a more widely used unit, is called electron volt, okay? So electron volt is the energy of, it's a unit of energy, not potential, okay? It sounds like a unit of potential, but because it has volt at the end. But the electron is not a prefix, okay? It's a combination. Electron volt is a combination. So this is a total unit. It's a whole unit for energy, okay? So what is the definition of this unit? Is the change in the energy of a charge of magnitude E moved from through a potential difference 1 volt, right? So it's very easy to convert it to joules if you want, right? You just convert the electron, right? Because this is a charge, right? You do charge times potential, you will get energy. So just replace this E with the amount of charge it represents, right? So this becomes coulombs and 1 volt, right? And then you just get this. Okay, so 1 electron volt equals this amount of joules. So very straightforward, the connection between these two units. So this is not SI units, but this is widely used in atomic or subatomic scale. Now, as I said, we have shifted our focus on this potential, like what we did with the electric field, right? You see that we spend a lot of time working with the electric field, right? Excuse me. Superposition principle, Gauss's law, right? And we did a lot of practice. Now we're gonna work on this potential, which is similar to electric field, right? Because once you have potential, you have a theory for potential. You can always calculate the potential created from any electric field. And then if you want to find a potential energy, easy, multiply that by the test charge, okay? Now we're gonna start with the simplest case. What is the simplest electric field? A uniform electric field, right? Okay, let's start with the uniform electric field. A uniform electric field, let's first draw it out. The easiest way to set up a uniform electric field, parallel plates, right? You grab 2 plates, make sure they have the same size, charge them with opposite charges, the same amount. Then the electric field between them, it's always almost uniform from positive to negative plate, right? So if this is the electric field created between 2 parallel plates, okay? So we want to find expression for the potential in uniform electric field. That's our goal, right? So let's just take a look at some cases, and then we're going to combine our conclusions, okay? So the first case is this. Let's just pick a point A here and another point B here, and then the path between them is just going to be parallel to the electric field lines, okay, like this. So if you use this definition, you would do this, VB minus VA, negative sign, from A to B, E dot dr. Now, how do you calculate E dot dr? You can just use the definition of dot product, or E dr cosine theta, pretty much like Gauss's law, okay? Now, in this special case, electric field is in that direction. What is this dr? This dr is the infinitesimal displacement, infinite small displacement in the direction from A to B, right? If this is from A to B, the infinitesimal displacement is going to be this guy, right? And in that direction, very, very small element, okay? So well, I zoomed in so you see what I mean, okay? Then that's going to be every dr, right, in the same direction. Now you see that in this special case, you can take out E. Don't forget the negative sign is still there. Cosine theta, what is the direction between the E and the dr, right? Remember, this theta angle is between these two vectors. E is in that direction, dr in that direction. So that's going to be 0 degree. And it's going to be the same, right? If I have the path between A and B always parallel to the electric field. So I would have E cosine 0, take them out, right? So you see that we always start with the simplest case. And then dr. Now this is going to give me E times 1. What is the integral over dr with no function in it? Well, that just means you add all these little displacements together. When you add all these little displacements together, what do you get? You get the displacement between A and B. That's just a distance, right? So if this distance is d, okay? So that's going to be our conclusion. Very nice. So if that's the first case, if the displacement from A to B, I have a uniform electric field, right? That's what we're doing now. And I have the displacement from A to B totally parallel to the electric field lines. So the potential difference between them is going to be E times d with a negative sign. Okay? Then, let's see. How do I use this conclusion? Okay? So this is VB minus VA. By looking at this equation, I want you to tell me VB and VA, which one is going to be larger? Well, if this is negative E times D, apparently VA is going to be greater than VB. Right? Then, so VB smaller number minus a larger number is going to give you a negative number. Right? So this is a general conclusion. Okay? Electric field line, you see that electric field line is pointing in that direction. Okay, and in that direction, the potential always decreases. Okay, so if you pick any 2 points along an electric field line, in the direction of the electric field lines, the potential always goes down. Okay, and this is going to be general conclusion because you can always apply this between any 2 points, right? Even if the distance is very, very small. Okay, so along the direction of in the direction of the electric field lines, the potential always goes down. You always get a negative sign. Okay, so this is a very useful conclusion. Again, this is one of the conclusion I would say you can remember because that's going to help you figure out which one's larger, which one's smaller. Okay, in the electric field. Okay, so even if I have an electric field like this. Not uniform, but this conclusion is still true. If I pick a point C here and pick a D here, and then the electric field is going this way, and I ask you, which one is at higher potential? You don't need to do any calculation. If you see the direction of the electric field lines, D is at higher potential, okay? Okay, I don't know the numbers, but D is always going to be higher than C, okay? And then you can still use gravity to help you to understand, okay? If I rotate this thing 90 degrees, what do I get, right? If I rotate this thing 90 degrees, I would get this. So I would get electric field in this way, right? Now A is above B, obviously, right? This is these are the 2 plates. This is pretty much like gravitational field, right? And if you define gravitational potential energy this way, A is definitely at a higher potential than B, right? Because the height of A is definitely larger than the height of B, right? So if you ask me, if this is gravitational field, you ask me A is above B, and then you ask me which one has a higher gravitational potential. Of course, A is going to have a higher gravitational potential than point B. And then gravitational field lines are going down because gravity is down, right? So in the direction of the field lines, the potential always decreases. So this is a general conclusion, and it's a very useful conclusion. But it's only true for potential, not for potential energy, because we're going to see this Q0 can be positive or negative, right? It can reverse the sign, okay? So this conclusion is only true for potential. In the direction of the electric field lines, potential always goes down. Always goes down, or vice versa. If I know the potential goes down in that direction, electric field must be in that direction, not in the opposite direction. Okay? So this is a very useful conclusion. And then this is what we just derived, right? If there's 2 points and the displacement between them parallel to the electric field lines, you just do E times D and with a negative sign. Now let's take a look at another case. If I still have this electric field and then created by 2 parallel plates. Now I pick 2 points, A here and then B here. So the displacement from A to B, this is a displacement. It's going to be perpendicular to the electric field lines. So what is now is the potential difference between them. Let's do this. It's going to be VB minus VA, negative sign E dot dr. That's the definition. Now let's use the definition to find that. And this is a special case, so we don't really need to evaluate anything. So it's still going to be E dr cosine theta. But now E is a constant, uniform electric field, take it out. Now cosine theta, it's going to be the angle between E and dr. Electric field is in that direction, right? This is still the uniform electric field we're using. Now what is the dr? That's going to be the small displacement element you pick from A to B, so it's going to be like this. This is a dr, or this, in the direction dr. Okay? So now you can see what is the direction, what is the angle between E and dr? 90 degrees, and it's always going to be 90, right? You pick this dr, 90, dr, 90, 90, 90, 90. So you will always get a cosine 90 for every point. So take it out. It's a constant, the theta angle. It's not a variable. Now I don't even need to do anything, right? This cosine 90 is going to take care of everything, 0. Okay, so that means VB minus VA equals 0. So VB must be equal to VA. So that's our second conclusion, a special case. If there's a electric field, okay, uniform, and then I pick 2 points and I draw the displacement between them. If the displacement between them is perpendicular to the electric field lines, the potential at these 2 points is going to be equal. They will have the same number. Again, it's going to be easier for you to understand if I rotate this in 90 degrees. If I rotate this in 90 degrees, what do I get? I get the electric field down. I get the point A and B here. Right? So that's going to be the displacement between them. Now imagine this is gravitational field. Of course, A and B, they will have the same potential, right? Because gravitational potential is defined as G times H. They have the same height, right? If this is gravitational field. Of course, they will have the same gravitational potential energy if you define potential energy, that gravitational potential that way, okay? But they're not going to have the same potential energy because you can't even talk about potential energy if you only have 2 points, right? You have to have some object. Right? So I can place an object 5 kilograms here, 10 kilograms here. They will not have the same potential energy, right? Because potential energy depends on the potential and the object you bring into these points. But potential is unique, right? Potential is determined by the source. So if I compare the potential of these 2 points, equal, always equal, right? Okay? So that's easy to understand, okay? I hope. Okay? So it doesn't have to be like these 2 points, right? You can pick another B, like this A and this B point here, right? or here, right? As long as they are on a plane perpendicular to the field lines, so if I pick this plane perpendicular to the electric field, any point on this plane is going to have the same potential, right? Again, rotated 90 degrees, you will get this. Imagine this is gravitational field. Any point on this plane, they're going to have the same height. Of course, they will have the same potential, gravitational potential, right? Electric field, the same, right? So it doesn't have to be a line, right? If you can find a plane perpendicular to the electric field lines, any point on this plane is going to have the same electric potential, right? So any point on this plane is going to have the same potential in gravitational field, of course, right? Because they have the same height, right? So, and then we call them equal potential surface, okay? So, and then I believe in one of the labs, you're gonna do that, okay? You're gonna find the equal potential surfaces, all right? So the equal potential surface, of course, it's just gonna be a plane you find on which the electric potential is the same everywhere, right? And the equal potential surface, it doesn't have to be always a flat surface, right? It can be spherical or be any shape, as long as it's the potential, the surface is perpendicular to the field, okay? So that you evaluate this integral, you always get a cosine 90. So the potential is going to be always the same everywhere, okay? So in this case, if it's a uniform electric field, the equal potential surface is going to be a perpendicular plane everywhere, right? Flat surface, okay? So that's the second case, okay? Now let's take a look at another case. So it's still a special case, but now A and B, the displacement is not perpendicular or parallel. It's going to make an angle with the electric field, okay? So in this case, I'm going to still use this electric field. Now this is point A, this is point B. So the displacement, if you want to draw that, that's going to be this line, right, from A to B. A straight line. So that's the displacement. Now, how do you calculate the potential difference between these 2 points using the definition? Okay, the same definition, potential difference between B and A, it's going to be this. Now, E dot dr, it's going to be E dr cosine theta, right? Now, I can take out E. I can also take out theta angle, but this theta angle is just not 0 or 90, right? It's going to be, so if this is dr, right, this is the direction of dr, because dr is just the every small element you pick along this line, right? This is dr, this is dr, this is dr, okay? So what is the angle between dr and this E? Well, that's just going to be this angle, if you call it theta, right? But this angle is going to be a constant, so still not a variable if this is uniform electric field, okay? So I can still take it out, but it's just not a special angle. So let's leave it there. Can be any angle, right? Now integral over dr. But again, if you integrate over dr and nothing is in there, you just get the total length, right? So in this case, you just get E cosine theta and the distance between A and B. So it's going to be this distance, right? And then if you do that, you realize that if I draw another point here, C, and then I make a right triangle, so let's call this C. So this DAB times, so there's a right triangle here, right? This is a hypotenuse. These are the two sides. DAB times cosine theta is just going to give you this distance, right? So if I put these two guys together, so I can make it a little bit simpler. It's going to be E times DAC. If I make another point here called C, right? To help me visualize the difference, the connection between A and B. So that means if I want to find out the potential difference between A and B, I can actually find out the potential difference between C and A. and that's going to be the same because B and C, they're going to have the same potential, right? And which is the true from this conclusion, right? See that the displacement between B and C perpendicular to the electric field. So from this conclusion, of course, B and C, they will have the same potential. So the potential difference between A and B is going to be the same as the potential difference between A and C, right? You do VB minus VA, it's going to be equal to VC minus VA, okay? So now we're going to use a different notation here. I'm going to call this distance parallel distance. I'm going to draw some two vertical lines there. So the conclusion is this. If A and B, the displacement between A and B makes an angle theta with the electric field lines, you can still do negative E times D. But now this D is the distance between A and B, but you're going to project it onto the direction of the electric field, right? So imagine this is X direction. You're just finding the X component of this vector. Right, so you just project it into the direction of the electric field, okay? So we call that D parallel, the parallel distance, which is the distance in the direction of the electric field, right? The distance between A and B in the direction of the electric field is gonna be this distance. So this is a D parallel, okay? So now we can actually summarize all these three cases, right? So actually this is gonna be our final conclusion. Right? Because if you make this theta angle 90 degrees, okay, the D parallel is going to be equal to, no, if you make it 90 degrees, that's going to be 0, like this. If you make it 0 degree, the distance is just going to be the distance between A and B, right? Excuse me. So the conclusion is this. If I have a uniform electric field, and I want to find the potential difference between 2 points. So totally arbitrary, you pick 2 points. The potential difference is always going to be this, okay? But okay, how do I know which one's higher, which one's lower, right? I just label them A and B. What if I label them B and A, right? So this is not how I'm going to remember this conclusion, okay? Well, you don't need to remember this conclusion. This is how I'm going to use this conclusion. My conclusion is this. The absolute value of the potential difference between any 2 points in a uniform electric field, it's always going to be E times the D parallel, okay? So if I have 2 points in a uniform electric field, if I want to find the potential difference between them. First of all, I need the electric field, like 5 newtons per coulomb. Then I'm going to find the parallel distance between them, which is the distance between A and B in the direction of the electric field, okay? So if you call the direction of the electric field X component, so you just find the X direction, you just find the X component of this distance vector, the displacement vector, okay? So the value of the difference is going to be this. But then how do I know if A is higher or B is higher? I take a look at the direction of the electric field lines, right? And then I can determine if A is higher or B is higher. Then that's going to give me 2 options. So I can pick, right, if this is true or this is true. So that's how I'm going to use this conclusion, because I don't know how you're going to label A and B, right? Okay, is A always on the left, B always on the right, right? Is A always at the top, B always at the bottom, right? No, I don't know. So how do I know which one minus which one is going to be negative sign? Okay, that's what I'm going to do. So whatever these 2 points are, the value of the difference between them is going to be E times the parallel distance. Now take a look at the electric field lines, because I learned that electric field lines is always going to be from a higher potential to lower potential. Right? So if I calculate this value and then I see this, this is A, this is B. Of course, VA, it's going to be greater than VB in this case, right? So if I calculate the difference between them, it's E times d parallel, say 2 newtons per coulomb times 5 centimeters, right? So that's going to be 0.1 volt, okay? Now, then I know that I should write VA minus VB, it's going to be 0.1 volt, not VB minus VA. That's how I'm going to use that conclusion, because I don't know which one you should call A, which one you should call B, right? If I see this equation, okay? So that's how I'm going to use that conclusion. Now let's take a look at an example so we can apply this conclusion. So that's the example on slide 13. Let's take a look at that. So we still have the uniform electric field. Now let's see what we're doing. Okay, 2 charge plates with 2 centimeter spacing, okay. So the distance between them is 2 centimeters, okay. And then I know the left plate is negative, the right plate is positive. Okay, so that means the electric field is always going to be, it's going to be from the right to the left. If you want me to draw the direction of the electric field between these 2 plates, right? Now, a proton and an electron are released from rest at the middle point. We want to find the proton's electric potential energy when it collides with one of the plates. Okay, so let's first take a look at the proton. The proton starts from rest at the middle point, so it's going to definitely feel a force, right? Because it's positive charge, the electric field is to the left, so it's going to feel a force to the left, for sure, right? And then this is going to be a constant force on it, right? Because the electric field is uniform, so it's going to keep moving, and with the acceleration, so it's going to get faster and faster, right? Okay, so it's going to reach this plate. So we want to find the potential energy of the proton at this point, okay? Remember, potential energy and potential, they're connected, right? They're connected by this definition. So if I can find the potential on the left plate, right, I should be able to calculate the potential energy. I just multiply the charge of the proton and the potential on the left plate. And the charge of the proton, we already know that's the little e. Okay? So all I need to do is just find the potential on the left plate, right, of the left plate. So, okay, if I want to find the actual value of this potential at a certain point, the problem needs to give me a reference. So the problem says, assume the potential of the middle point is 0. So we're going to assume this is 0 volt. This is our 0 reference. Again, you can assume any point as a 0, right? You can even say this is 1,000 volts, 2,000 volts. Doesn't matter, right? As long as you give me a reference point. So all I can do, so what I'm going to do is this. I'm going to use this reference, and then I'm going to calculate the potential difference between these 2 points, right? Using this conclusion. And then, so I'm not going to use this. I'm going to calculate the value of this difference. And then I'm going to take a look at direction of these lines, so I know that if it's going to be V left minus V middle, or middle minus V left, right? So let's see. This is conclusion is this. It's going to be E times D parallel, right? So, okay, electric field, is it given? Okay, it is given. The electric field 2 times 10 to the 5th newtons per coulomb, right? So that's the number I plug in. The distance, so you need the distance between these 2 points you pick. The problem gives me 2 centimeters. Is this distance the distance I want to use? I'm not sure, okay? You should read these questions careful, okay? It's not like there's a distance from the problem. I'm going to plug it in. You're not doing any thinking, okay? I need this distance. right? Because I'm calculating the potential difference between this point I want to calculate and the reference point, so I can determine this potential at this point, right? So this distance is the distance I plug in, all right? And it is the parallel distance, right? Because this is the direction of the electric field, is horizontal. So I only need the horizontal distance. That's the distance you plug in, right? So it's not going to be 2 centimeters. It's going to be 1 centimeter. So once you find out that, okay, the problem tells me this is 0 volts. But how do I know if this is true or this is true? Right? Now you see that you don't even have A and B, right? You don't even know how to label them as A and B, right? So you will have two options, right? And how do I know which one is true, right? Because it's going to make your answer different. You want to get the right answer. You don't want to get the wrong answer. You take a look at the lines, right? We learned that the electric field is always in the direction of decreasing potential, right? If you go in the direction of the electric field lines, your potential, the potential always goes down, right? That's going to help you figure out which one is the right one. And then you're going to rearrange this equation, you can get the potential on the left plate, right? Because the problem already gives you the potential at the middle point, right? 0, okay? All right, so now you can pause the video and then do the algebra, okay? All right, so now let's finish that. So in this case, so first of all, I multiply these two numbers. What do I get? I get 2,000 volts, right? Now, which one is the right relation between them, right? Which one is higher, which one is lower? Direction of the electric field lines in that way. So that means this point, even if I don't know any number, this point is going to be higher than that point, okay? So it should be V middle minus V left equals this number. So this is wrong, actually. I should pick this relation. Okay? So the V middle minus V left is going to be 2,000 volts, in this case, from the direction of the electric field lines. And then the V left is going to be actually V middle minus 2,000. Okay? Now I'm going to use the number, the value of this V middle, oh, in the problem is 0. So that's going to be negative 2,000 volts. Okay? So that means the potential of the left plate is going to be negative 2,000, right? If you tell me you call this is your 0, right? If you tell me V middle is 5,000 volts, but this is still true, right? You see that the difference between them is going to be unique. Right? If you tell me this is 5,000, okay, you call, oh, now let's make this 5,000. Okay, that's fine. 5,000 minus 2,000, 3,000 volts. I'm going to tell you the potential of this left plate is 3,000 volts. If you say you call this guy 5,000, right? Or if you say, let's call this negative 4,000. If you call this is negative 4,000, this is still true. Okay, this is still true. The difference between them is still 2,000. But if you tell me this is negative 4,000, okay, so the potential of the left plate is going to be negative 6,000 volts, right? So see that my answer depends on the reference point you provide. Okay, it depends on the 0 reference, right? It doesn't even need to be the 0 reference, as long as you give me a reference point, right? But the difference between these 2 points doesn't depend on that. Okay. So now, based on this reference point you give me, I calculate the potential of the left plate, right? So now I can go ahead and plug it into this relation between this electric potential and electric potential energy for this proton, right? Because for proton, the electric charge is going to be E and the potential is there. So there's no absolute value sign here, so you don't make anything positive, you don't, okay? You stick to these definitions, this equation, these theories we learned. You don't just drop any negative signs, remove any negative signs based on your own judgment, okay? So I'm gonna do the proton, right? On the left plate, it's just gonna be the charge of the proton, which is E, the potential I just found, multiply them together. If there's any negative number, keep it there, because I don't see any negative sign in these definitions, okay? That's going to be negative 3.2 times 10 to the 5th. No, negative 16. Okay, that's my answer. And if you tell me a different charge, right, and different ion, this number is still going to be true, right? Once you have fixed the electric field and the reference point, the potential on the left plate is going to always be negative 2000. But if you want me to calculate the potential energy of a different particle, I'm going to just change this number, right? So you see that once you have the potential, calculating potential energy of a different test charge you bring in that point, it's going to be very easy, okay? But calculating the potential is the hard part. You need to do that first, okay? So that's this. Now let's take a look at the next part, okay? Now there's also an electron here. An electron is also released at the middle from rest. So I know that the force is going to be opposite to the field because the electron is negative. So the force is going to be to the right. Constant force, constant acceleration. So it's going to be moving to the right plate. It's going to become faster and faster because there's an acceleration, right? So it's going to collide with the right plate. So now the question wants us to find the electron's electric potential energy when it collides with one of the plates, so it's the right plate. So I want to find the potential energy of this electron at this point. I'm still going to do this. The charge times the potential, right? What is the charge of an electron? Negative this number. So you're going to plug in a negative number, okay? Because there's no absolute value sign here, okay? I'm not going to make any negative numbers positive. Now, what is the potential at this point? Okay, you're going to repeat everything, right? So I'm going to erase this. So again, the problem already tells me reference point 0, right? Middle point, so I would do this, repeat what I just did with the left plate. So if I can calculate this by using E times D parallel, and then I use the direction of the signs to figure out if this is right, okay, which one is right. And then I can go ahead to find the actual value of this potential at the right plate, right? So again, electric field is the same because it's a uniform electric field. What is the parallel distance used? You're going to use this distance, right? This is a middle point, this is right plate. You want a distance in the direction of the electric field, that's the distance. So this is still 1 centimeter, okay, in this question. And then you figure out, okay, you take a look at the direction of the lines. Which ones had higher potential, which ones had lower potential. You know which option is the right option. Then you go ahead and find the potential on the left, right plate. Plug it in. You can find the potential energy of this electron when it reaches the right plate. Okay? Now I can pause the video, do the algebra. All right, so let's see. This number is still going to be 2000 volts, right? Because you get the same electric field at the same distance in this question, right? Now, which equation is the right equation I should pick? The direction is in that direction, so the right plate and the middle point, which one is higher? Well, of course, this right plate is going to be higher because that's the direction of electric field. Always decreasing potential in the direction of the electric field lines. So I know that I should pick this one instead of this one. So this is wrong. I don't pick this one. So right plate and wireless middle is going to be 2000 volts. Okay, now I'm going to use the reference point you gave me. Okay, so the right plate, it's going to have a potential V middle plus 2000. Okay, tell me this reference point, right? Okay, you tell me it's 0, good. Then that's going to be 2000. If you tell me it's 1000, okay, the potential is going to be 3000. If you tell me this is negative 2000, the potential on the right plate, 0 volts. right? You see that? It totally depends, the actual value totally depends on the zero reference or any reference you provide me, okay? Once you provide me a reference point, then the value is gonna be unique, okay? And then you're gonna do the same thing for the electron. Electron has a charge in negative E, keep it negative, and then potential, it's gonna be the potential on the right plate. All right, multiply them together, okay? Don't remove any negative sign. You will get this. Okay, so both of them have negative potential energy. Potential and potential energy can be positive or negative, okay? Don't be confused by this name energy, okay? It's because I don't know what negative energy is in real life. Doesn't mean that we can't define negative energy in physics, okay? We can still define that, okay? So that's how we use this conclusion to find the potential of any point, okay, in a uniform electric field, and then go ahead and use the relation between the potential and potential energy to find the potential energy of a test charge. Right? Finding the potential energy of a test charge is going to be the easy part. Finding potential is the hard part. Okay? So I'm going to stop here for this video.